out our fourth to last set of notes. I will tell you, parametric equations is not hard. I promise. We're going to go back to taking some derivatives, taking some integrals, but it's going to be of like nicer equations, and I promise there won't be infinitely many of anything. So we're going to do that. We are splitting unit 10 over spring break, but it's actually at a place that makes a whole lot of sense to split it. So 10.1 and 10.2 are parametric and vector, very much similar topics. Vector is kind of like this with position, velocity, acceleration, like a physics overlay. And then when we come back, we're going to be doing polar, which is entirely different, but we kind of just squish all of it together because it's just applications of derivatives and integrals. So there we go. Do you guys know what happened on Friday?
No.
Round two?
Yes, round two. What about like not just this class?
Quarter.
It's a B-Day.
The quarter ends.
Oh, so like a party or something. I don't know why.
You're missing something.
What? I know she was gonna say that.
Oh, there it is.
Just put the spider. At least 10. As long as you
I just want to do like a staff.
And then I have to study for calc, German. Oh, I have to register for the thing.
So other reminders. Oh yeah, if anyone wants to do the mock test, I think I only have 7 friends coming right now. So
What now?
for the mock test,
What was it, 19th or 18th? Is there
any
any
after
after spring break?
there's one after, one before.
Is I'm not available throughout the week.
It's like during.
All right, I need my notes.
And then we can get started.
18? Wait, when are the dates?
It's the Monday or this coming Saturday.
What time's our actual test? 8 a.m., right?
8 a.m.
Oh wait, yeah.
I will lure you in with breakfast
Sorry,
though.
what days do you have again?
May 9th.
9?
I think so. Is that the Monday?
Yes. It's the day after I get back.
Monday, April 18th.
Oh, you're doing it Monday.
You're gonna study all day at Hershey Park.
Oh, that's the day we have last day of spring break.
I mean, there's really.
All right. Are we ready? We do not look ready at all.
Oh, really?
All right. That was good. All right. We're going to talk about parametric equations today. What a parametric equation is, or a set of parametric equations, is we're going to take one equation that's like y equals stuff with x's in it. We're going to split it into 2 equations. So we're going to have an x equals equation and a y equals equation. You can kind of think of this, sometimes in physics they do this, where they split like horizontal motion and vertical motion. That's kind of the idea of what we're doing right here. We're splitting into an x direction, a y direction, and we get a new letter because each of these equations is going to be set up in terms of t. I like to think of that as time, because of most of the vector stuff we'll be doing. So we'll have an x equation for time, a y equation in terms of time, and there we go. So we're going to start by just figuring out what the heck does this look like to graph this. I will say the first page, while cool, is not anything that would be tested on the AP exam, because as you'll notice, we won't be doing any calculus, at least until the second page. Then we're going to do some stuff with derivatives and one application with integrals, and we'll be done. So I'm going to graph one of these and show you how to what's called eliminate the parameter, and then you're going to graph the other one for me. I'm going to make an XY chart to graph because that's the easiest way to start graphing. You'll notice that I don't just have an XY because now I have to plug in values of t. Thrilling. All right, what do you think the smallest value of t I will want to plug in is? 1. Why 1, Griffin? What? Okay, so x, I can't square root negative numbers, so I would like to plug in the thing that would get me 0. So square root of 0 indeed is 0. What will the y coordinate be? 3. Last time I checked, 1 plus 2 does equal 3. Perfect. All right, what other t value could I plug in? 2. All right. 2 minus 1 is 1. Square root of that is 1. 2 plus 2 is 4. Now I'm going to start graphing these. Actually, we'll graph them in a second. Now, would I want to plug in 3 if I'm graphing? Probably not. I could. 5 might be better. So that's 2 and 7. Now, I know this is going to go off the graph, but let's just do one more. What would your next point be? All right, so let's talk about how to graph it. We're still graphing on the XY plane. So T is kind of irrelevant after I have my points, but these are the points that you want. So the first one I would be 0, 3. Then I'm getting 1, 4, 2, 7, and 3, 12 is going to be somewhere way up here. The only difference is when I graph, parametric is kind of cool in that the kind of direction of the points matters here, because the t value is giving me a specific order in which the points were going, kind of thinking about direction. So one thing we add to this graph is a little set of arrows to indicate which direction we graphed the points in. There are ways to make the direction switch depending on what kinds of equations you set up, especially if you set them up with sine and cosine, they can get a little cute and you can switch directions. But here we have this kind of half parabola looking thing. Now, you might say, how do you know that's a parabola? I can do what's called eliminate the parameter, which is just a very fancy way to say I can get this to be an equation that says y equals stuff with x's in it instead of having 2 separate equations. How I would do that is choose one of the equations to solve for t and substitute it in the other equation. Does anyone have a strong preference about which one we should solve for t? All right, cool. It doesn't really matter which one. So I'm going to do y minus 2 equals t and plug into the other equation. Now, usually we have our equations in y equals stuff with x's in it. So I'm just going to solve this for y really quick. So I get y equals x squared plus 3, which I'm not at all surprised to see. That's a parabola. It has a y-intercept of 3. That looks like half a parabola with a y-intercept of 3. One thing you might be noticing is this graph and this graph don't entirely match, and that's because of the way this set of parametric equations is set up, we actually get a domain restriction because of that square root. So what x values am I allowed to get out of this set of equations? Positive, greater than or equal to 0. So you just might have some sort of domain restriction. That's not going to be super important to us to try to figure out. We'll usually be already getting an equation or working with an equation, and we won't have to worry about that. But just so you know, it can pop up. All right, so what I'd like you guys to try to do is graph one for me. So you're going to take the one down here and graph if you're feeling spicy. Try to eliminate the parameter. Notice you are given an interval of t on which to work. So personally for me, when I was making my chart, I used all of the integer values between and including -2 and 3. So I plugged in -2, -1, 0, 1, 2, and 3. Feel free to plug in less, plug in more. And if you don't know how to connect your dots, you can use eliminating the parameter to check what shape it should be. So I'm going to give you not an hour and 18 minutes. Let's try like 4. Wow, it's wildly quiet in here. You guys are the only class I have to teach today. Because I tested last block and I didn't teach Zach anything this morning. He took her test on computer. I wasn't here last class. Should try. Oh, I should have eaten my lunch at lunch. If you want, so I'm gonna say eliminate the parameter, and you'll see why. That get it into like X's and Y's. A football shape? It's oddly specific. Okay, 5, 1.5. Does that help? I think it looks like a side. I can't help you there.
How do you connect the dots?
How do you go there?
Choose our own way or?
No.
So
The arrows are how I connect them. So remember, you had a direction in which you connected.
Oh, right. That's about all the arrows on the line.
For parametric, yes, you should.
Oh.
I wouldn't, because we're ending our interval there.
So you need the lines, the arrows up here.
No, so because we're kind of on a specific interval, we can kind of use that interval to create.
If you had the arrows on both ends, if it wasn't on the interval, that'd be good.
I don't know. I'll look it up.
Unless you do the inequality thing.
The eliminating the parameter like this.
Yeah.
We were gonna do it in a second, yeah. If you want to try, you can. Oh, you have 5 seconds. Ha! All right. So do you at least like my graph? Cool. All right. If you were going to eliminate the parameter, which equation would you solve for t? I think I would do y just because it looks easier. Again, either one should work theoretically. So I'm going to do x equals 2y quantity squared minus 4. Now, to get the idea of this picture, I'm not going to solve this for y because this does not look like a function. So I don't think getting into y equals will be very productive. This does not pass the vertical line test. But we can kind of see why we drew a parabola here, because we've got x equals like y squared. So you do get that actual sideways parabola shape. One advantage to some of the things we're doing in this unit, both parametric and polar, is we'll be able to graph things that aren't functions with relative ease. So that is kind of one of the benefits of parametric. All right, so now that we've kind of learned what a parametric graph does, how they kind of interact with each other, let's talk calculus. We're going to do the derivative part. We'll take a break, and then we'll do a very, very short integral part because there's not too much integration that we're going to be doing, at least today. So I want to show you what the derivatives are. I will tell you, I think the first derivative makes a whole lot of sense. The second derivative makes kind of a little bit of sense. So I'm going to show you a couple of ways to make sense of it, but it probably will be the most highlighted thing on this test because everyone always forgets. So I'm going to give you kind of algebraic representations of why these things work the way that they do. But I think the slope makes a whole lot of sense. If we're looking for dy dx, the problem with taking these derivatives is our functions are in terms of t. So when I take a derivative of x, I'm going to actually be doing like 2t there. It's going to be a little bit weird. So if I want the rate of change of y with respect to x, I'm going to do the rate of change of y divided by the rate of change of x. It's kind of exactly what I would hope it would be. It makes a little bit of sense if you think kind of, I'm using air quotes for algebraically, because I know these aren't fractions, but let's just treat them like that for a second. If I took dy dx, not dx, dt from the top, and instead of dividing it by dx dt, I multiply by its reciprocal dt dx, what does it look like would happen if we were using algebra rules? The dt's would cancel and I would get dy dx. Now that's not exactly legally how that works, but I think it gives a good representation as to kind of intuitively why this works. Since we are dividing two things, we're going to assume that dx dt isn't equal to 0. We won't be asked about that. Now, the second derivative gets a little bit creepy, so I'm going to show you two ways to make sense of this. In the end, most of my students end up kind of memorizing this as a trick, but there are two relatively good ways to think about it. The reason it gets weird is because when I take a derivative of my first derivative, it will be in terms of t, but I kind of want to take this derivative with respect to x. So that mismatch of letters is what's going to kind of get me in a more complicated situation. So what you'll notice is we're going to find our first derivative by doing derivative of y over derivative of x. Then when we find our second derivative, we'll be doing the derivative of that derivative divided by another dx dt. And that divided by dx dt is a little bit weird. I'm going to show you a couple of different reasons why that is the way it is. So let's first do it kind of like I did the first one. I'm going to take the numerator, d dt, dy dx. So that's the derivative with respect to t of whatever I got for the first derivative. That will be in terms of t. And let's again pretend that I am, instead of dividing by dx dt, multiplying by its, air quotes, reciprocal. Here, I would argue again, the dt's could cancel, and I could kind of morph this back into the derivative with respect to x, stealing the d from the front, the dx from the end of dy dx, which does get me my second derivative. Now, if that is not satisfying to you in terms of like canceling differentials, I will show you another way that we can think about it that I think makes a little bit more sense in this first example. Ready to take derivatives? Yeah, and it's because we're going to have this in terms of t. So when I'm finding my rates of change, like think of dx, I can't do dy dx here because y isn't in terms of x. It'll make more sense in a sec. Ready? That's like take the derivative of the thing inside here. That's what that notation means. All right, so let's first find dy dx. Now, this is one thing I do. When I'm finding dy dx, I always find dy dt first, like vertically, if I'm going to align my work vertically, because the amount of times I have divided the wrong way is stupid. Also, y is a little bit harder here. What is the derivative of 4t to the fifth minus 6t cubed plus 3? You guys agree with Rashawn? Wow, wasn't that refreshing? Polynomial. To be fair, we have been doing polynomial derivatives in Taylor series, just infinitely many. All right. I have not been a good saleswoman this year. No one has been taking my favorite units. All right, what's the derivative of t squared plus 9? 2t, isn't it? This is a little bit. All right, let's talk about dy dx then. I'm going to take dy dt, which was not 3, 20t to the fourth minus 18t squared, and I'm going to divide it by dx dt, which was 2t. Now, if I were just doing dy dx, I could certainly keep it like that, but I'm about to find the second derivative, so I do want to simplify this. How could I simplify this? Yeah, I'm just going to like divide by 2t. So 20 divided by 2 is 10. T to the fourth divided by t cubed. 18 divided by 2, 9. T squared divided by t. All right. So we're going to now find the second derivative. There are a couple of ways to do this. I'm going to show you one that kind of gives a little bit of a justification as to why we're going to divide by that dx dt again. Most people will probably not do the question the way I'm about to do it, but I do want to justify one different way why I'm going to divide by that dx dt. So let's say I am taking the derivative with respect to x of my first derivative. So the derivative with respect to x of my 10t cubed minus 9t. Now, one thing I want to point out, do these letters match? d dx of 10t cubed minus 9t. No. So I need to think back to like the very beginning of AB calculus when I had letters that didn't match. Let's say it was like 10y cubed minus 9y. What did you do when you were taking a derivative of stuff with y's in it? You added dy dx at the end, or just like related rates when you were doing derivatives with respect to t of stuff that wasn't t. So essentially we're going to chain rule the letter that is not x. So what would the regular derivative of 10t cubed be? 30t squared. And then because t is not x, I'm going to have dt dx. The letter I have versus the letter I'm taking the derivative with respect to. All right, let's see who is listening. What's going to come from negative 9t? Perfect. All right, do we notice that these have something in common? All right, yeah, let's factor that out. So I'm going to take dt dx and factor it out. And I don't really know what dt dx is. I do know what its reciprocal is, though. So would you agree this is the same thing as 30t squared minus 9 divided by dx dt? Hey, that's where that divided by dx dt comes. Now, we already found dx dt. That was 2t from way long ago. So I have 30t squared minus 9 all over 2t. Now, you are more than welcome to do the question that way. Conceptually, I think that works really well as to why I'm dividing by dx dt. Most of my students in the past have been, let's say, not willing to write that much, aka just a little lazy. So they would rather do a little memorizing here. So what you can do is you can do your derivative of your first derivative with respect to t. So that's your 30t squared minus 9. And they just know that they can divide by dx dt. So their work might just look like dy dx equals 30t squared minus 9 all over 2t from what they had before. So just for memorizing that you have to divide by that dx dt at the end. Yeah, exactly. Which is totally fine. If you're going to memorize it like a formula, that's totally fine. And this is wrong. Say that again, sorry.
The reason that we had to do the dt dx's
Mhm.
when you're like taking the derivative is because it says d over dx.
Yes, so we're taking a second derivative with respect to x when our derivative is in terms of t. So that mismatch of letters there. Yeah. So I'm kind of, instead of multiplying by a reciprocal, I'm dividing. So if I like divide by 1/2 or multiply by 2, so kind of taking that and making the reciprocal on the bottom. So just like if I were dividing by 2/3, I could multiply by 3/2. Cool. All right, at the end of the day, if you want, take the derivative of the first derivative divided by dx dt. I'm just showing you a couple of ways to know how to do that. All right, now that we know how to take a derivative, what's the most classic problem? Let's write a tangent line. It's been a while. What do tangent lines look like? What do lines look like? Yeah, y minus y1 equals. Yeah, we could write it in mx plus b if we wanted. I like point slope a little bit better. All right, so what two things do I need to be able to find this equation? I need a slope. That's probably calculus. I need a point. Now, one fun thing about parametric that's not fun at all, for my point, do I have an x value or a y value right now? No, I have neither of them. So I will need to do some trig. And I need to plug in that t value. Do you guys want to do the x and y first or the slope first? All right, let's do a vote like this is democracy. Who wants to do the point first, the x and the y? Who wants to do the slope? All right, let's. No one votes. All right, let's just get some trig under our belt with the x and the y, because my guess is not a lot of you remember sine and cosine of 2 pi over 3. So no. All right. So let's start with x is 5 sine of 2 pi over 3. We got to figure out where that is. So anyone remember where 2 pi over 3 is? What quadrant? Number 2, yes. It's over here.
It goes one less, one more, and then one less than double.
What?
Because it's one less 2 pi over 3, and the next one is like 3 over 2 or whatever.
All right. Do we even know what our two choices of numbers are? Disregarding negatives. 1/2 square root of 3 over 2. Do you know which one's bigger? Square root of 3 over 2. All right. So I always think of triangles and longs and shorts. So sine, that's the y value of the point, right? So what am I going to plug in for sine of 2 pi over 3? Square root of 3 over 2 with the 5 is 5 root 3 over 2. Because this side is bigger than this side. You tell me. All right. Nina's claiming that the 1/2, which is the shorter one, should be negative here. Do you guys think she's right? She is. We went left. So the point right here, if we were talking about this point, would be negative 1/2 comma square root of 3 over 2. So we're going to have negative 3/2 for our point. Now, no one said your trig has to be fast. My trig for this problem is not that fast either. I can't just blurt out what the sine of 2 pi over 3 is. I have to think it out as well. Did I think it out a little faster in my head? Maybe, but I've been doing the unit circle for a heck of a long time. So, all right, so we got an x and a y. What else do we need? A slope. You guys cool if I just do a derivative of y over derivative of x instead of listing each of them separately? So what I'm going to do is dy dt over dx dt. I'm just not going to list them separately. All right, y is 3 cosine t. What's the derivative of y with respect to t? Nice. Someone whose name is not Nate Gribben. X is 5 sine t. What's the derivative of x with respect to t? Sick. We're just taking the derivative.
Yeah, but you're saying, what are you taking the derivative of though? Oh, just that, okay, that's what I was
You good?
So the thing on the bottom is what the variable is?
Yes. All right, I'm about to plug in t equals 2 pi over 3. I'm using some sweet Leibniz notation to do that. So saying dy dx such that t equals 2 pi over 3. I'm going to plug in, let's see, sine of 2 pi over 3. I'm going to cheat on our work over here. What was sine of 2 pi over 3? Square root of 3 over 2. And then cosine was -1/2. Now, by all means, I could use this as my slope unsimplified, but I don't like the way it looks right now. So I would like to simplify it a little bit. What? No, but this is probably going to be a multiple choice question, so you'll want to know how. What would you simplify out of this? What do you mean the two? Yeah, the halves can go away. What else can go away? The negatives. So I'm going to call this slope 3 root 3 over 5. Thanks. All right, what do we think the answer is then? Uh-huh. Ooh, plus 3 over 2. Cute. Beautiful. Yeah, so it's not the nicest equation ever, but they don't have to be nice. How beautiful. All right, the last one. Yeah, we're like almost over. Yeah. All right. You think this is cute? All right, this one's even cuter. All right. Remind me one more time. How do I find dy dx for parametric? I have a fraction. What goes on the top of it? And dx dt goes on the bottom. All right, just a reminder. So the last kind of derivative application that we're going to see today without the overlay of physics is we want to be able to find points of horizontal and vertical tangency. So let's think about, can you graph a horizontal line with your arm? Perfect. What is the slope of your arm? 0. All right. So if I want a horizontal tangent line, I want my slope to be 0. If my slope is this fraction, what should be 0 if I want that big old fraction to be 0? The top, right? So I essentially want dy dt to be equal to 0. All right, let's find dy dt. What is the derivative of t squared minus 8t plus 9? That is an absolutely thrilling equation to set equal to 0. I'm going to do it in one step because I'm so brave. Do you agree with t equals 4? Yeah. Wow. Have I answered this question at all, though? No, they did not ask for a value of t. They asked for a point. How the heck am I going to find a point? Plug it in. So let's see how fast I can plug in. This is 12. Nope, that's not how you square 4. 48 minus 24. Is that right? Did I do it wrong? I'm doing x. How do your points go? My points go x comma y. All right, 16 times 3 is 48 minus 24. And then let's see, this is 16 minus 32 plus 9. So what is that? That's -7. And this is 24, I know. So 24 comma -7. So really the only thing about parametric that's kind of annoying is sometimes we have a couple extra steps to get our final answer going. All right, I'm going to try to give you guys a graph of this equation real quick so I can show you what it looks like in parametric. Will you guys do the vertical part for me? What am I going to set equal to 0 for the vertical part? the bottom, which is dx dt. Make sure you get a point, and I'm going to show you a graph. Oh, that is not what I wanted. Ti.
Yeah, but that was do you want it to be in front? Oh, it's vertical. Got it.
We don't want the bottom to equal 0, right?
You do want the bottom equal to 0. Because what's the slope of a vertical line?
Oh, 1.
No.
Oh, wait, no. Vertical.
Can you run up and down a vertical line? So it's actually not a number. It's a word.
Undefined.
There you go. How do you make a fraction undefined?
Oh, 1 over 0.
Something over 0. So you want to set the bottom equal to 0.
Oh, that's this.
Zoom. 6. Wow. It's probably better to write is, but I don't think I'd get too mad either way. Did you guys get an answer already?
-3,
Whoa, hold on. All right, I think I like -3, 2 as well. We good? All right, before we take our break, I just wanted to show you a quick picture and kind of how you can do some of this stuff on the calculator if you want. So you may have noticed earlier this year, if you picked up one of my calculators, if you went to y equals, it might have looked a little bit weird where there was an x equation and a y equation. Math Analysis was kind of doing this at the beginning of the year, or not the beginning, a couple months ago. So if you want to graph in parametric equations, you can go down and where it says function, that's normally where we live most of our lives, in function. You can switch it to parametric. You can also switch it to polar, which is what we did before. Or what we're going to do after break, excuse me, not what we did before at all. So I plugged in the x and the y equations. You get a couple of new options with your window. You can set kind of like that first equation, or the first one that you guys graphed on your own, where there was an interval of time for the t. This one also has an interval of time. This one's currently graphing between t equals 0 and t equals, I think that's 2 pi. This step is how often it kind of checks to graph a point. So that's some fraction of pi. I'm not really sure why it's doing pi. I think it's because the second example we're going to graph today looks kind of uses some pi for the trig. If I graph this, you can kind of see what it looks like. Let's trace some of our points. Now, when we use trace here, it does want us to plug in a t value. So I'm going to plug in t equals 4, enter. That was our point of horizontal tangency. Does that look like it would have a horizontal tangent line? Yeah. All right. Where was the t value for the vertical one? Was it 1?
Yeah.
All right. Notice we have our -3, 2 at the bottom. Does that look like it would have a vertical tangent line there? Hey, it almost is like it makes sense. Yeah.
What's the difference between trace and like, isn't there like calc x equals or something?
So if you want like a value.
Oh, yeah, that.
Yeah, value is really the same thing as trace. I don't really know why you would want, it does the same exact thing. I'm not really sure why that's an option, but whatever. Emery. No,
It's so good.
I don't. My husband does though, and one time we didn't have pineapple, but he wanted pineapple on his pizza, so he put a nectarine on it. It was, he did not like it. He put nectarine on pizza. But I think he also did like bake. It was like a whole lot of substitutions. No, I'd rather have hot sauce. Have you never done like Frank's with pizza? All right. While we're here, let's take a break. We have very, very little left to do with parametric. And then we'll go back and talk about interval and convergence for a little bit. Take 4.
I'm worried about the.
Nina.
Are you gonna have my test grade so I can do round
Done. Oh, it's already done.
So I can come whenever.
Yeah. Mm-hmm.
I went to the bathroom today.
Also,
Do you think I should improve my instructor? She was supposed to put on my Instagram page. Or should I just?
I'll shoot her an email.
Okay, cool. Thank you.
Thank you. Mm-hmm.
Do I follow these steps and look to answer this question?
Mm-hmm. Yeah.
Can I bring my round 2 today during early release?
Sure.
Okay.
I think I have it highlighted. If not, I can highlight it real quick.
If not, it's okay.
Oh, no, no,
I only have early release on B days, and I know we're doing 2 tests later this week,
no.
so I didn't think about it until just now.
Yeah, I think I highlighted the rest of them this morning. If not, it'll only take me like 2 seconds.
Oh, her?
Would you be able to grade the test into like a low?
Oh, that,
You know how they do like low?
Yeah.
Can I come in the morning?
Yeah. Are you not going to be here on Friday? So
Get that like.
yeah, we'll do some super common mistakes on Friday, like at the beginning of class, right before we do round 2. But if you want more, just let me know.
Wait, how did you not know?
I'm plugged into the X and the Y with the T equals 4. So I took my T value here. So 4 squared times 3 is 48 minus 6 squared.
Tell me this is cute.
All 80 for Nolan bars.
For these, if this was a -1, I could have just canceled it out.
Florida.
No. Oh, yeah, because the absolute value bars, yeah.
With this, can I separate this 3x in and then times 3x?
Yeah.
Oh, okay.
I just saw it on my computer.
I get this.
When? Saturday. Only Saturday. She's going to be Oh, she's going to be She made it sound like August.
30 seconds already?
Yeah, we can also get laser.
Let's go to Friday with
Oh, Nina is in town. I thought you said that morning, so. Yeah. Tell them that we're retreating them now. Yeah.
All right, we ready? We only got 2 questions left. 2. And they're not hard. All right, does anyone remember me ever saying the words arcline? S equals something. Oh my goodness, that's more memory. Now, does anyone remember the something? Oh, there was a square root inside of it. There was a 1 plus. There was something. Why am I writing this below the line? Hold on. I'm annoying myself. All right. There was a square root. There was a 1 plus, and there was something squared. Do we remember what was squared? The derivative. So whatever the derivative of our function was. All right. That was a couple of units ago, so that might be a little bit blurry. I'm about to write down what this is for parametric graphs. Now, I think it intuitively makes a little bit of sense. You'll notice I didn't write down any room for you to prove why this is the way it is. But if you see this formula and you're like, I would like you to prove that to me, I am more than happy to do so. I just didn't think you would need to write it down. So I'm going to write this down, and you're going to decide, do you want to algebraically know why it is true? It is okay if the answer is yes. It is okay if the answer is no. The dx is not in the square root. Good question. All right, so I'm going to write, just to be really explicit, t equals a and t equals b. So these were x values up here. We're going to use t values here. Still going to be a square root. But I have two different derivatives now. So instead of 1 plus my derivative squared, I'm just going to do each of the derivatives squared and add them together. What was the point of the 1 plus? It kind of popped up out of the algebra for it. I don't know if I have like a good geometrical interpretation. It's probably working off of like a unit vector kind of thing. Does anyone want me to prove why this is true? No? If you, okay, I'll do it. If you don't care, you have about 4 minutes to take a nap. So I didn't give you room because I don't want you to write it down. Just I'll announce when I would. Yeah. Oh, we definitely have time. I just don't want you to write it down. Why this is the way it is.
Why that's the formula?
Why that's the formula. Yeah. All right. The one thing you have to accept for this to work is you have to accept that this is the formula for arc length. But I already proved that to you. So if you don't, then go back. So here we go. I'm going to now replace, excuse me while I go and not do bounds. Why is everyone and their mother sick right now? It's disgusting. All right, I'm going to replace our derivative with what we called our derivative from the beginning of the notes. And now I'm going to roll. So I am going to square the top and square the bottom of that because that's allowed. Oh, P.S. I'm not really going to ask you a lot of questions. I'm just going to demonstrate. Apologies if that is annoying. You like being lectured? All right, now I am not loving the fact that this is like 1 plus a fraction. I would like it to be like one big fraction. I want a common denominator. That common denominator is going to be this dx dt squared. So that 1 would be like dx dt squared over dx dt squared. Yes? All right. Then I'm going to have my dy dt here. All right, just like I kind of distributed the squared from this step to this step, I'm now going to distribute the square root to both the top and the bottom of this fraction. So I'll have a big square root of dx dt squared plus dy dt squared. All over now dx dt squared and then square rooted. Since squared and square root are kind of opposites, I'm going to go with just dx dt on the bottom. Now, as has been the theme for a lot of these simplification sort of things, instead of dividing by dx dt, I am going to multiply by its reciprocal. which is dt dx. Have I been writing the wrong? I have been writing the wrong one the entire time. All right. So this was our original formula, so this should be dx. And that's important because when I multiply by dx, these guys will cancel, and then I'll be in terms of t. So it's kind of the reasoning behind why that formula is the way it is. Now, in the end, are you going to derive that yourself? Absolutely not. I like to think these formulas are very, very similar. It kind of makes sense to me since we have to do two derivatives for parametric. We got to do two derivatives in our arc length formula. No, because of the addition in the middle. All right, if you tuned out, time to tune back in. We got only two examples. Now, these examples are almost always going to be set up, but do not evaluate. If you're not seeing it from the formula itself, you're going to see it in a second. This is going to create something that is so long, we definitely will not integrate it by hand, but kind of so long that it gets annoying to do it in the calculator even. So, yeah. So here we're going to set up our integral. Do you guys agree with Rashad that good bounds would be 0 and 4? Sick. All right. I'm going to draw a absolutely enormous square root. I'm not even going to put the dt on the x. I'm going to run out of room. And I'm just going to do my derivatives. It actually doesn't matter what order I go in because we're adding and that's commutative, but I'm just going to do dx dt first. What are your thoughts on dx dt? All right, where is Rashad's front 5 coming from? Chain rule. This is an excellent way to see if you know how to do chain rule for the AP test givers. So there's one of them. Thoughts on, yes, squared comes from the formula. Then thoughts on dy dt? 3 cosine. Times 2t, again, chain rule, squared, dt at the end. Again, this is kind of an annoying thing to have to write out. It would be super annoying to put in the calculator, and odds are we would forget something in there when we're plugging into the calculator. So the vast majority of these, even the multiple choice, are like set up but do not evaluate. So the choices may be like different sets of equations. The dt is outside of the square root. Yep, that's it. Yep. Yep, set up, and then it specifically says do not evaluate. What?
I know. I didn't think that was that.
All right, let's make it longer. All right, what's kind of glaringly missing from this set of equations? This one has no bounds, but I would like to think about it. We have some trig in here, an epicycloid. I'm going to show you a picture of it in a second. It looks kind of like a butt, like 4 butts together. What? No, that would be a good guess though. All right, let's think. So, question. Sine and cosine are like cyclical, right? Eventually they come back around and do the same thing. How long is like think like all the way around the unit circle? How long does it take to get all the way around? 2 pi. So I'm gonna guess, and we're gonna verify that the bounds would be 2 pi on this. Now, if I gave you a question like this, there is no way in heck that I would expect you to know the bounds without a calculator. So let me just show you how you can play around with this. So I'm gonna go back here. I'm gonna type my 2 equations in, and it does. It looks like a butt. So it'll look like a clover at first, but all right. So 5 cosine of t minus cosine of 5t. P.S. When you're plugging these in, if you ever do want to plug them in the calculator, if you press the X button, that's why this has like X, T, theta, N, is you can plug in different things. 5 sine t. No.
Are we gonna have to calculate on this?
Probably. No.
Okay. Yeah.
All right. So I'm gonna look at our window really quick. So this is gonna graph from 0 to 2 pi, but we'll mess around and see if that's actually accurate. I was zoomed out before, so I'm gonna press zoom. Actually, I might zoom square this guy to make him a little bit better. And then I'm gonna zoom in.
Whoa.
All right. So maybe you're not convinced that I kind of drew this right. So I'm just going to shift and I'm going to make the T max just pi for a second to verify to see if that's going to go like only half the way around the way I think. It's a but. All right. So it does look like 0 to 2 pi will work. And that's going to be a theme. When we hit polar, when we come back, we're going to have to think a lot about how long a graph is going to take to go all the way around. 0 to 2 pi is generally a good guess because we're working with sine and cosine for trig functions. So when we go and set this up here, what do you think 0 and 2 pi are going to act as in my integral? Bounds. All right, 0 to 2 pi. All right, this one, absolutely humongous, square root. All right, thoughts on dx dt? All right, we're starting here. What's the derivative of cosine? Negative sine, so negative 5 sine t. All right, thoughts on the derivative of negative cosine 5t? Plus sine 5t. Why did I leave a space? For chain rule, which is a 5. And then squared, yes. All right, I'm going to add in the middle. What will my dy dt look like? Five cosine t minus squared. dt at the end outside of our parentheses. And this, it's just too big. We don't want to plug this into the calculator. So you'll often see this phrase of setup but do not evaluate an integral expression. All integral expression means is just something with an integral in it, expression meaning not equation, so it doesn't need to have an equal sign in it. That's it. So this gets a little bit more interesting, and what we're going to be doing next time called, they call it something different, but it's really going to be just a physics overlay on parametric equations. We're going to be talking about vectors is what they kind of label that section, but it's going to be a lot about like horizontal motion and vertical motion, kind of splitting those two with parametric equations. All right, what I would like to do to kind of finish out my talking for today is to do a little thought process. Now, I'm going to steal this from the end of the 9.2 notes. If you don't have those, I'm going to pull out the whiteboards if you want. Can you remind your neighbor, and while I get out the whiteboards, you can remind your neighbor, then I'll have you remind me, what an interval of convergence is. You may want to use words like center and radius of convergence to talk about it. We're going to be talking about these questions right now.
Sam, let's be honest. Whatever you say this, he knows the answer after he sees it. He's like, oh, it's t equals 1. It just popped in my head. Good one.
No, we didn't. All right, can anyone tell me what an interval of convergence is without using the word interval or the word converge? Half points if you can use the word converge. Yeah. Like that. Fair. So converge is a hard word to not use, but the radius of convergence gives me a distance from the center where I know everything inside that radius will converge. So let's talk about this series for a second. What is the center of this power series right here? No, -3. All right. We're given two pieces of information. And I'm going to kind of let you run with these for probably about 4 minutes. I know that I have my series converges if x equals -8 and diverges if x equals 6. So I find it most helpful, this is the only hint I'm going to give you, to draw a number line with my center at the center. Though it's a number line, it could be wherever you want. And kind of putting these numbers on either side. It's on the back of the 9.2 notes, or you can just put it somewhere. So I want you to figure out, and we can play sit, stand, hover if you would like. Let's change that. I think there's more must be trues. So we'll make this stand. No. That would be no fun. All right, so I want you to look at these numbers right here, and I want you to think about what our interval of convergence is. That tells me how far I can go from the center to know that everything between those places and the center converges. I want you to tell me if these statements must be true, may be true, or cannot be true, based on the two pieces of information I gave you and knowing that the center is -3. I'm just going to let you roll with it for about 4 minutes. If you are super stuck, think about it first. There's one of them that you should be able to answer if you have been here. All right, what do you think of like? Maybe you want that's not on the thing. So this guy converges at -8. So what do you think? If I say like if x is present, -3 would be that's closer. It's closer to the center? Yeah, so if I'm closer to the center than this.
Oh, I check you through
So that happens on both sides.
Last people together, or just me and you would just go together, or more. Where do you plan to do this? He's just asking for the free chat.
It doesn't
free
say
one,
that
but
start
I kind of want some 3 days. No, I just have to go and ask for times I do. And then, based on what he says, we'll ask the group chat if there's any problems. Oh, Tricky, did you get back the schedule? Did you get back the schedule? Okay, give me a quarter of 8.
All right. What do you know about the center? What do you know? Does that converge or not? All right, so this always converges, and we're being told this converges, right? What do you think is true about anything in here? Okay. And what do you think about like something that's close to the center, but like on this side? Yeah, because don't remember how we made the interval?
Yeah.
When we add and subtract.
Oh, yeah.
Okay, so let's talk about something like.
-3, and that's where.
So your 6 definitely diverges.
Yeah.
So you can do something.
So if you do like 6 plus -3.
All right, you got about a minute more to ponder and think. I don't know if we're going to play sit, stand, hover because everyone's looking at me with deer in the headlights eyes. We can talk it through. We have a couple of minutes. There may be a question like this exactly on your test, but you know.
I don't want to put him in Shelly today. Of course, you'll have to remember, but it's all asked.
All right, let's talk it through really quick. So, what did we say is always true about the center of our series? What happens at the center? We always converge. So this works, and we've been told that -8 works. Now, if we think about our interval of convergence, it's giving us a range of values where we know we converge. So what do you think is true about any number I would pick in here between -8 and -3? We would converge. Now, I don't think there's any numbers there, but we have a number like 1, which would be right here. Now, why do you think I drew those little brackets on the bottom? Yeah, we have an interval of convergence. If you remember how we made that interval, we usually got our radius of convergence and added and subtracted to make that interval. So how far away is -8 from -3? 5. So what's 5 in the other direction? 2. So I know that all the way up, that's not what I wanted to write there. 5 makes us to 2. So what do you think about x equals 1? Will the power series converge at x equals 1?
Yeah.
Yes, and this must be true. It is closer than something we already know converges. Is there anything else we can conclude from that? What do you guys think about the last one? The power series diverges at x equals -3. Yeah, that cannot be true. That's the center. I can't write right now. Oh my goodness. That view is even messed up. Oh, I'm just so nervous. All this public speaking. All right. So let's think. The x equals 2. Now, think about this. This is another endpoint, right? So what if that was our radius of convergence? Does one endpoint impact what the other endpoint does? Or do we have to test them both every single time? We had to test both every single time. So this one may be true. We're not quite sure. It might be. Oh, there's a question exactly like this on your Unit 9 test. Very similar numbers, probably. All right, now let's talk about x equals 6. X equals 6. We're out here. We know this definitely diverges. So how far is that away from -3? 9. So go in the other direction. What do we think? -12. That would work. All right. So if 6 diverges, I would argue anything farther away from that should be something we know about. What's anything farther away from 6? What should it do? It should also diverge. So do you see any that you could answer? -13. So it says the power series diverges if x equals -13. What do you think? May, must? Must. That is farther away than something I already know diverges. All right. What are your thoughts on x equals -9 and x equals -10? They could be. We're not exactly sure how big this radius of convergence is. So they're kind of in this like question mark spot in here of something that is farther than I know converges, but closer than something I know diverges. So these both are some maybe truths. Yep. All right. I just wanted to talk about those because though we kind of have the idea of what an interval and radius of convergence is, I am going to put one that's very explicitly like this one on the test because I think it's cool logic. So you'll see that. When is our test? Wednesday. If anyone's not going to be here on Friday, I would encourage you to try to get your round 2 in, but it's not super important because the end of the quarter is not until Friday, and this test isn't even going on this quarter. So I still have a couple of minutes because it's advisory day. Yeah, I know. I was like all worried, and then I was like, oh, you got like 7 minutes left. So let's do some announcements. You guys are going to announce them to me, so I don't receive emails. Do we have a test today? Yeah. Yes. All right. Tell me about our test. When is it? Wednesday. Is round 1. When's round 2? Friday. Now, Friday, I will go over a few common mistakes on Friday, but if you're looking for a more extensive review, you can certainly pop by in the morning. What else am I going to get from you before spring break? I would argue there's probably 2 things. Problem set. Tell me about due dates for that. Problem set.
Wednesday, extra credit. Friday, due.
Yeah, that's what I did for AB. So it's like plus 2 out of 20. Or not out of 20. Out of either 30 or how many questions are on it? 15? 16. Oh, why did I do 16? That's annoying. Whatever. All right. What else? Oh, Q3 work. Several of you. So this is Friday. Yeah, 4:03 p.m. All right. Several of you have round 2s that you should be doing. I updated the gradebook this morning during 5th block, so you can check on there to see if you're missing anything. Round 2s need to be done by then. Any other missing quizzes, tasks, problem sets need to be turned in by then. I am going on spring break. I don't want to talk to you about quarter 3 on spring break. The only exception to talking to you on spring break, mock exam. If you are interested in taking the mock exam, there's not very many people signed up right now, but I want to give the opportunity to everyone who's wanting to do it. If you just want to come in, I'm not going to judge your score at all. I really don't care. I want you to experience what an AP Calculus test feels like because it doesn't feel that good. It's not supposed to. It's supposed to be hard. So if you want to come in and see what it feels like, I can give you a projected score, or I don't have to if you don't want to know. We're going to be doing 3 different sessions. There's one on the Saturday, right after the end of the quarter. So this coming Saturday at 9, or I'm holding 2 different sessions on Monday, the 18th. I will make sure the free responses are going to reflect parametric and vector and not polar. So you'll only not be able to do a couple of multiple choice questions, if that. So it's a good experience. I highly recommend it if you have the time. If you don't have the time between now and break, but you do want to investigate what that feels like, fill out the Google form. There's an option to say like other times. Michaela. Yeah, so the last thing I'm going to say. I'm going to roll around now since it's like the end of class. This is a Taylor series review for the test we'll be taking next time. Answer key is already posted. If you have any questions, feel free to let me know. This is a completely optional experience. I believe this is a test from a different teacher in the county, which is why it's formatted a little differently, but it has some really good questions in it. Specifically, some better Lagrange questions than the ones I put on the problem set. So the test, I was looking at rewriting the test this morning, looks pretty similar to this if I had to say. So I'm going to drop these. If you have any other questions, let me know. Otherwise, I will see you next class for our test and perhaps turning your problem set in.
Question.
Let me. When the test going on. Still going strong? Yeah. Ever since I got the money.
I was thinking of derivative when we're talking there. Yeah, we're cool.
I just.
Oh my God.
Second to last test of the year.